Okay, so then we are going to start today. So last week we introduced the particle filter, or the basics of particle filtering. So how to do recursive Bayesian state estimation in the context of non-parametric distributions. And we especially looked into the sample-based representation. The idea was to use a set of samples to represent the state space and the distribution over possible states. And we can see every sample as a Poth hypothesis. So every sample represents one possible state the system might be in. And then the probability distribution is given by a sum over the states of those samples together with a weighing term and a Dirac distribution in the state of these samples. And the key advantage of these sample-based representations is that we are very flexible with the type of distribution we can represent. So we are not restricted to Gaussian distributions, for example, as this was the case for the Kalman filter or extended Kalman filter, but we can easily represent multimodal distributions in here. And today, I would like to look into the SLAM problem. So how can we actually address the SLAM problem using particle filters? So just as kind of a two-slide repetition of the particle filter, what we discussed last week. So the particle filter is a non-parametric estimation technique. That means I don't have a parametric form, like a Gaussian distribution, for example. So distribution in parametric form, which I use to represent my probability distribution. But I use samples, or weighted samples, and kind of the number of samples that fall into a region of the state space is proportional to the probability of that area. That's kind of the key idea behind that. What we haven't discussed in detail here, but what I at least said last time, is that the particle filter is very well suited for doing state estimation in low-dimensional spaces. If we go to very high-dimensional spaces, that is more challenging. Why? The reason is that I need a sufficient number of samples to cover, let's say, the areas of high likelihood or regions of high likelihood in my state space. And if I have a high-dimensional state space, I need a huge number of samples. And therefore, these approaches work well in low-dimensional spaces, 3, 4, 5, 6 dimensions, something along these lines. But they do not work well in whatever 100-dimensional spaces. That's kind of one of the problems of the particle filter, that it gets computationally so inefficient because I need such a huge number of samples that the approach simply doesn't scale to higher dimensions, at least not in its standard direct form. The particle filter itself consists of 3 steps, which we discussed. The first one was a sampling step, where I draw samples from my proposal distribution. The second step was an importance weighting step, which was the result of the importance sampling principle, which tells me that if the proposal distribution is not the distribution I want to approximate, and this is typically the case, then I need to do a correction step, so to say, and compute an importance weight that accounts for the differences between the target distribution, so the distribution I want to approximate, and the proposal distribution, the distribution from which I've drawn my samples. And the last step was the resampling step, which kind of redistributes the samples and there's a high likelihood that a sample with a low probability is replaced by a sample with a high probability. So it's kind of this survival of the fittest-like principle in order to concentrate the samples in the likely areas of my state space. If you look to that in algorithmic form, we had these 3 steps here. The first one was I draw a new sample. So this is the J sample at time t from my proposal distribution pi. And for the localization example, we used the odometry motion model to generate the next generation of particles. So we say, how did the pose of the robot evolve given that we executed a command? That's what we use the proposal distribution for. And that will also be the proposal distribution in the SLAM context, as we will explore that today. And then the second step is the importance weighting step. This was a direct result from the importance sampling principle, which says that if I draw samples from an arbitrary proposal distribution, but I want to approximate a target distribution, I need to assign a weight to each sample, and the weight is given by the target divided by the proposal, both evaluated in the location of the drawn sample. So a sample where, for example, the target distribution has a very high likelihood and the proposal distribution very low likelihood, this gets amplified by getting a high weight. This just accounts for the differences between the target and the proposal. And the last step was the resampling process, with just drawing samples with replacement. So I draw sample I proportional to its likelihood. I do that with replacement. I simply draw J samples. And that's the resampling process. And after resampling, all the weights are set to 1 divided by n, because then they are, again, then the locations of the samples are distributed according to the target in the end. That's what I wanted to have. So this was the key steps of the particle filter, which we discussed last time. And what I use is a set of weighted samples, x and omega, in order to, or w, x and w here, in order to represent the state and the weight. And this is my sample set. And if we now think about the SLAM problem, so we move away from localization, where the state space was an x, y, theta location, and we move towards the SLAM, where we want to estimate the position or trajectory of the robot, and together with all landmark locations or the whole map, then our state space moves from a 3-dimensional state to a high-dimensional state space. So we have here the poses where the robot has been and all landmark locations. So in the beginning, and for localization, we just had x, y, theta, so a 3-dimensional state space. And here now we have a much higher dimensional state space. So as I said before, the particle filter is an effective representation for low-dimensional spaces. But this turns to be not the case in our setting over here. So this is a high-dimensional state space. If I have, let's say, 1 million landmarks and the long trajectory of the robot, I have easily 2 million plus the length of the trajectory dimensional state space, which is orders of magnitudes larger than what a particle filter with a finite number of samples, or with a number of samples that I can actually represent in a computer system, can actually handle. So there's no way of applying a standard particle filter sampling the overall state space. That's kind of one of the key limitations why it actually took quite a while until people discovered a way, or not discovered a way, but found a way to use particle filter-based SLAM, or build particle filter-based SLAM system. And the key idea is, let's have a look to the individual state variables that we have in our state space, and let's see if we can actually exploit a dependency between them. So if there are a dependency between the poses and the individual landmark locations that we might exploit, what do you think? If I ask this question, the answer is too obvious, but then the next answer would be, what is a possible dependency we could exploit? So we have the positions of the robot during data acquisition, x1 to t, and we have the locations of all m landmarks. It's a high-dimensional state space. We want to cover this state space by samples, but we cannot cover the full state space using a sampling technique, so we have to do better. So do you see any way of exploiting a dependency between those variables to do that in a more efficient way? Is there any dependency you know between these variables?
No.
Which one?
You can assume they're independent.
You really think the poses of the robot and the landmarks in the environment are independent of each other?
The pose with the robots, the landmark with each other are independent.
I strongly disagree with that. Otherwise, this whole lecture would not take place, because then would be two separate estimation problems, and simultaneous localization wouldn't exist. So there must be something else.
Yeah, the robot pose is surely dependent to the maps to the landmarks,
Mm-hmm.
and the landmarks to each other also.
Yeah. If you think about the lecture on grid maps that we had last week, what dependency did we exploit in there?
I wasn't there.
Okay, anyway, the others? So what was mapping, the grid mapping approach that I presented, the work of Moka